And today, as it's been introduced, I'm going to be talking about Stardust. And this is really the question of where everything comes from. Where do all the elements that make up us and everything else come from in the universe? And the answer is stars, which is kind of an interesting question. And we'll talk about the elements that are important for us in terms of life, which are things like carbon and oxygen and iron. But then, we always all like gold, silver, and platinum. So you should ask, where do they come from? So let's move on. Hang on. I just first introduce myself a bit more, which is, yes, I'm Associate Professor JJ or Jan Eldridge, as Simon said. I prefer either JJ or Jan. My pronouns are she, her, and them, they. I'm an astrophysicist and I study exploding binary stars while exploding the myth of a gender binary. Just because I'm always open about the fact I'm transgender, which means my gender does not align with the sex I was assigned at birth. And I always introduce this because in this talk, we're going to talk about stars. And we're going to talk about stuff that we're all going to go, wow, the universe is amazing. It's such a complicated place. I just sometimes talk about myself to remind everyone that people are actually kind of all complicated too, as is biology. So it's like I chose the easy thing. I chose to actually do astrophysics because that's really easy compared to like trying to understand how biology and people work. Another important question I always like to talk about is also, why do I do astrophysics? This is always interesting because people think like, oh, you must have got a telescope when you was young or something else. The answer is no. I just watch too much science fiction. So my father always used to read books like novels by A. Van Vogt and Isaac Asimov and Arthur C. Clarke. And I ended up, when I was growing up, watching a lot of Doctor Who. So, Sylvester McCoy, the 7th Doctor, was my Doctor, although I really like the 2nd Doctor. People used to think I looked a lot like the 10th Doctor, David Tennant, but fortunately I've regenerated. So, back when I had blonde hair, I looked more like Jodie Whittaker. So why is it fun to know about science fiction? Because it's a great way to actually use science fiction when you're talking about stuff. And I actually use science fiction in some of my other talks. For example, looking at the planets of around other stars, what do we see in the science fiction programs? What do we actually know? But also, what about the basic physics? How does Eve and Wally move around in the universe? Which is always quite good, a little bit of fun to try and think about things like that. Hang on, I just want to see my preview slide so I know what's coming next. You can also trust what I'm going to say because not only do I watch a lot of Doctor Who, I have met 4 of them. So here's me from a time warp. Back before. It was great because I tried to get my head of department to pay for this ticket because it was $400 to get the premium pass and get this photograph and their autographs. But he never said that. So yeah, but it was well worth the money. And they all look as grumpy as that in real life. Good to see that somebody has Tom Baker as their first Doctor. We can do a poll later on in the questions. Who's everyone's favorite Doctor? But let's get on to where we're going to talk about. So where we're going to talk about with this story of where does all the stuff around you in the room and in the universe come from. And our story starts in your chemistry lessons at school, which is where you would have seen something that looks a lot like this, which is the periodic table. Normally, the lanthanides here, which are this big group between the 2 and the 3, second and the 3rd column, are normally hidden off somewhere else. But this is how a chemist looks at something we call the periodic table, which is an arrangement of all the elements we know in the universe, all those that are possible and live long enough for us to be able to actually get some and understand them, going from the simplest, which is hydrogen, up to helium, and then all these other ones. And what they're arranged in, as you go from left to right, you're making heavier nuclei. So everything around us comes down to things that are called atoms. And in atoms, there are different elements, which are those different boxes on here. And that's because they've got different numbers of protons and neutrons at their center. And then they've got electrons which revolve around that nucleus, and that's what makes an atom. And you've got the same number of protons and electrons in each atom. And so when it says 1 here, that means that hydrogen has 1 proton and 1 electron, whereas helium has 2 protons and 2 electrons. And as you go down, right? So this is where we get all this variety. And it's important with the electrons because if you talk to a chemist, when they look at all the different elements, they think about those electrons because they're the things on the outermost parts of the atoms. They're the things where you can combine atoms together to form molecules, like water, where you have 2 hydrogen atoms with 1 oxygen. What we're going to talk about is, where do those elements come from, right? Did they just pop into existence? And what's the processes to how they come about? Because also when we look at this table, this doesn't tell us about how many of the different elements they are. This just tells us about, okay, because I mean, where did this come from? It was Mendeleev who realized, oh, these elements like hydrogen, lithium, sodium, they're quite similar. Helium, neon, argon, they're quite similar too. So we can put them into different columns. So these are chemically similar elements. So again, this is a chemist's periodic table. But what we can also look at is here. This is another one. It's quite old and it's not necessarily true, but it's a really good demonstration of, let's take that periodic table and make the size of each bit where each element is relative to its abundance on the Earth's crust, right? So you can suddenly see it looks completely different. Hydrogen is quite big, oxygen is huge, silicon's quite big, iron's quite big, calcium. But all those other elements, which are heavier because they're further down, they've got more protons and neutrons, are actually much, much rarer. So this immediately tells us something. We can ask some questions. Why in our universe? Why in our planet? Because there's a complicating factor is here. You know, our planet doesn't have lots of hydrogen because it's closer to the sun when it formed. And if we were to look at, say, the gas giants like Jupiter behind me, you know, that has a lot more hydrogen because of where it formed in the solar system. But if you look at these heavier elements, so everything beyond helium, so, you know, why are carbon and oxygen so popular, right? Why does the universe have so much of that? When, like, why is iron and silicon about the same amount? And so there we actually need to try and understand, and that's a different question. You know, chemists can't answer that because they don't study the universe and what makes the elements. And so to trace back to where this first question was actually, I mean, astronomers are always thinking about these questions. But this is the first paper where people really started thinking about it, which is this, it's a review of modern physics. So this is, I worked out, this is about 64 years old now, which is, it's really exciting to think how long we've known about this. And there was works done before this, especially work by Fred Hoyle, who's one of the authors. But the two people who actually came in this paper, because it's like synthesis of elements in stars, and this entire paper, it's many pages long, is all about setting out for the first time where the different elements come from. And so it's actually Margaret Burbidge and Geoffrey Burbidge, who were the first two people who really led this paper. Fowler and Hoyle did a lot of early work, but Burbidge and Burbidge actually worked together. And it's actually always nice to look at them together. And it's a really interesting story when you look at their career, because this was at a very early time in the, like, well, okay, 60 years ago doesn't sound that long ago. But there was a job that Margaret went for as the director of an observatory, and she got it, but she couldn't actually be employed because only men could take up the post. And so her husband, Geoffrey, who had another job, basically they swapped their jobs around so they could both work on the same problem. And it was funny because he was a theorist and he was meant to be a director of an observatory. And all theorists actually do is we go around, think and use computers and do calculations. We don't actually, I don't know how to use a telescope. So, you know, if I was in Calgary, I'd be popping down to borrow one of those and rent one of those telescopes so I could actually get some experience. But it's interesting, it's these two people really led the way, and it's a key point. They didn't just bring everything together, they made it accessible, and this paper is very, very accessible. And I'm going to actually show you, even though I'm going to put together things of the most recent astronomy we've been doing, I'll actually go back to some of their data because it's wonderfully clear the story they tell about how you actually try and understand where the elements come from. So let's go back to this plot, right? So here we are. So we had our chemist's periodic table. And now we come here where we're looking at the relative abundance for all the elements. But let's look at an astronomer's version of this periodic table, which is not so much how much the elements there are, but where they come from. Now, on purpose, I've actually colored out and blanked out some of the answers. And the only ones I've left there are Big Bang fusion, where the universe was formed about 13.7. I never can remember if it's 13.7 or 13.8 billion years ago, but you know, you'll forgive me if I'm 100 million years wrong. Where the universe was created in the very early universe, there was basically lots of hydrogen and some of it fused to helium. You got a little bit of lithium, but nothing else, because the universe didn't have time to make those heavy elements, which is why the universe today in general is about 75% hydrogen by mass, 28% helium by mass as well. Like in our sun, 2% of everything else. To an astronomer, we get a little hate mail from chemists because everything that's not hydrogen and helium to an astronomer is a metal. Which some of you may suddenly think like that's rather bizarre, but well, hey, it's only now recently we've been able to actually get abundances and more things to actually understand how everything fits together. Cosmic ray fission is just things like whizzing around the universe at high speeds and like breaking apart other nuclei. So that's where you can get your beryllium and boron. They're very difficult to make in stars, as is lithium, as you can see here. But there's lots of colors here. There's green, there's blue, sorry, lighter blue, orange and yellow. And that's basically where stars come from. I'll also bring up those gray ones because those gray ones are very radioactive isotopes. So if we have them on Earth, they're made synthetically. They're not, there's nothing that you can make those in stars because they decay away to nothing before they actually get into the Earth. For example, you can see down here, uranium, lots of that on the Earth because it's quite stable, but neptunium isn't, the next one over. This technetium one, keep an eye on that one because so many people kept on asking me about that. As we go through, I realized that's actually an important story to tell, and we get onto that. Okay, so let's start with the story of our sun, right? Which is always a good way. If you're ever talking about stars, the best thing to do is to actually start with the sun, because the sun is fairly typical. Most stars in the universe are the mass of the sun or just slightly less. The minimum mass for a star is about 1/10 of the sun's mass. The upper mass limit is actually somewhere between 100 and 300 times the mass of the sun. But when we look at the sun, we know it must be about 4.5 billion years old because that's the age of the Earth. And if we look in the interior of the sun, we know it must be very hot inside. I'll show you some of the evidence of how we know it's that hot inside. Outside of that, outside of the core, where it's generating the energy by nuclear fusion, putting hydrogen nuclei together to form helium, you have this radiative zone, and all that means is that's where the energy is being transported by light that's millions of degrees in temperature, so it's very, very bright, and you wouldn't want to look at it. And then you've got a convective zone outside where the surface is actually bubbling. It becomes easier to transport the energy from the core to the surface by moving the material. And we can actually see that if you look at telescope images, for example, up here at the surface of the sun, you see this granular type of lumpiness, and that's because the surface of the sun is constantly churning over from about 70% of the way out from its core. And there's lots of other things that goes on the surface. The wonderful thing about the sun is it's so close, we can see it in excruciating detail, and there's a lot of things we don't understand because we can see it in so much detail. When you look at stars that are very far away, because they're so far away, you can't see much detail, and so they're simpler. But it's always a nice place to go. But the point here to take is what's going on at the center of the sun. How can, if there wasn't any nuclear fusion going on in the sun, it would have a lifetime of about 20 million years. So that's how long it would take to start from a gas cloud and collapse down to nothing before it used up all of the gravitational energy just by contracting. And so to stay there stable for the billions of years, and in 10 billion years in total, it has to have another energy source. And that energy source is nuclear fusion. And so this is how elements really make all the elements other than hydrogen and helium. So actually, when you think about it, the first stars in the universe, if there was only hydrogen and helium after the Big Bang, must have only had those elements. Everything else has effectively come from stars. And what stars do is they do very similar to what happened in the early universe, but now, of course, it's slightly different because the time scales are longer. You take two hydrogen nuclei, two protons, you smash them together. One of them becomes a neutron, and you, at this time, because you're changing a proton to a neutron, you're changing flavor of the particles, and so you, where's my mouse pointer? There you go. You get a neutrino released, and an electron, a positron to take away the positive charge, which is just an antiparticle electron. And then the neutrino flies away as well, and you have deuterium, which is an isotope of hydrogen. So it's still got the same number of protons and electrons, so it would still be the same chemically, but it's a bit heavier. And then you can combine your deuterium with another proton, you get helium-3. So here you have two protons and a deuterium, and a neutron. You combine two helium-3s together, and you end up with two protons flying off, but you get your helium-4, so you get your next most stable element. So just to try and fuse a few words here, this is what I mean about elements, where you've got different numbers of protons, but different isotopes. For example, you've got an extra neutron or like a neutron too low. Yeah, if that makes sense. And the neutrons are there to try and hold the nucleus together, because actually if you had two protons together, they just want to push each other apart. It's not stable. You need the neutron there to glue the two protons together. But this is really great, right? Because I can tell you this and you can go, but Jan, how do we believe you? You know, you're just saying this. What's the evidence for this? Well, here's something interesting. If this is going on in the center of the sun, then we should be able to see neutrinos because, everything around you is made of protons and neutrons and electrons. But, there's also neutrinos, and actually these are being released in these nuclear reactions. And so if this is happening in the sun, there should be something like 100 billion neutrinos going through your finger every second. So if we move on, we can actually take pictures of the sun in neutrinos. Now, this is difficult, and Canada has its own experiments, and this in some ways has led the world, because if I remember correctly, you have a large amount of heavy water supplies somewhere. But basically, you have a big glass container, you fill it full of water. Neutrinos really don't interact like interacting with anything, right? That's why you've got billions going through you right now, and you don't feel anything. So you can have these big experiments where either a neutrino comes in, hits a molecule of water, and the molecule, all the energy is transferred to that electron or something within the water, and it zips off at close to the speed of light and makes a glow. There's also this other experiment over here, which is basically a big tub of dry cleaning fluid, and the neutrino would chemically interact with some elements and changing elements in a very, I mean, like we're talking 1 or 2 atoms being changed over the course of a year, but it's enough that you can work out what the neutrino flux is. And with the modern experiments like we have up here in the top right, that's an image of neutrinos. That's the sun, and you can see all the neutrinos coming from the core. It's not accurate enough to know how big the core is, but we know that the sun is producing neutrinos. So again, there's actually 2 pieces of evidence that nuclear reactions and nuclear fusion is happening in the sun. One is the age of the Earth just being 4.5 billion years old, and the other one is this neutrinos. I'll get onto the 3rd piece of evidence later. Okay, what's going to happen in the future? Right, so this is the sun now. The sun's a middle-aged star. It's halfway through its lifetime, and so you've got the. So this is my kindergarten explanation of stellar evolution. I love this slide. I know I need to change the colors. I've got red and green on. I'm really sorry if you're colorblind. I need to change this. I'll get around to it one day. But you've got your main sequence star burning hydrogen to helium in the center. Now, like anything that's burning through stuff, eventually you use up all your hydrogen. And we'll see in the future, the sun will develop this pure helium core. So the densities will be hundreds and thousands of times the density of water. The temperatures will be in excess of 100 million degrees Kelvin, but the star's center will be pure hydrogen. It will still have this hydrogen helium mix outside. And actually, one of the interesting things is this is when a star becomes a red giant. The core contracts, the envelope expands for complicated reasons. There's, if you actually read textbooks, you find lots of different similar explanations, but it's very complicated because the physics is subtle. But eventually, what happens is that as this envelope expands and the star becomes very big and cool, it's a lovely word, by the way, it's erythrogigantism. If you ever wanted to learn one new word, there it is. It's very difficult to spell, so I'm not going to try and do it. But eventually, while the envelope is expanding, the star's becoming cool, big, and red, the core is contracting. And as it gets denser, it also heats up. And eventually, whereas in our sun, it's taking 2 protons together to make helium, what happens in the center of the sun and other stars, they'll take 2 of the helium nuclei, because this is pure helium almost. And so you smash 2 helium nuclei together, and it doesn't stick together. They fall apart after about a fraction of a nanosecond. But that's just long enough, a fraction of a nanosecond, that you've got your 2 helium nuclei together, that another 3rd helium nucleus can come along, and you end up sticking your 3 helium nuclei together. And if you count up on the periodic table, you get carbon. Now, that's a really important element for all of us, right? Because we're carbon-based life forms. Carbon is so chemically useful. You know, there's an entire field of chemistry called organic chemistry, which deals with carbon molecules because they're that exciting. So that carries on. And eventually, when you get enough carbon, you can actually put another helium nucleus onto carbon and you get to oxygen. So what will happen in the future of our sun is not only will you have this helium core will eventually become a carbon-oxygen core, which I've labeled here in blue. And it will have this very thin helium envelope, and then this hydrogen helium envelope on top of that. Sorry, I should say helium mantle, because it's like a bit around the core, because this interior bit is very, very dense and very small. And eventually what will happen is all this hydrogen envelope will be blasted off. And you will end up with a white dwarf, which is just a carbon-oxygen core. Now, this is a problem because I've gone through this and I've said, okay, so stars will take hydrogen, turn them into helium, turn the helium into carbon and oxygen, which is great because that's for us, but it's all locked away inside the white dwarf. It never comes out. So how will our sun actually make elements that will go into the next generation of stars? Well, it's in this process when it's going from this big fluffy red giant with a carbon oxygen core to that white dwarf. And we see lots of stars doing this. And this is what they look like. And so in the center of each one of these, you can see a white dwarf. It's very hot, it's very bright, because it's basically the leftover core. But all this stuff you see around it is that hydrogen envelope, all the leftover stuff that didn't make it into the core because the innermost core is only about 10 to 20% of the total mass of the star. You know, that's all locked away, but all the rest of the material is thrown away. And what's really amazing is when you look at this, at the edge of the core, hang on if I go back, right? So you've got here this carbon-oxygen core. Well, at the edge of the core, here between the blue and the green, you've got helium burning still going on. And over here between this green and this red, you've still got hydrogen burning going on. So the core carries on growing and it produces a lot of energy and it's very unstable. And there's lots of mixing and stuff going on. I'm making this, it's wonderfully complicated. It's one of the most amazing things that stars do, that these two really close burning shells interact and make lots of elements. Not in great abundance, but lots of different elements, which is really cool. Now you're going to say, like, Jan, how do we know this? Right? There's always one thing to say things, but how do we know it? How can we tell you're not fibbing? Well, when we look at these things, right, they're light. They're throwing out all this light, which is amazing. We can take a spectrum of it. And they're emission line spectra. So they're very particular lines at very particular wavelengths. And now one of the great things is, if we go back to our periodic table, I'm going to show you another periodic table now, which is this one. Now, this doesn't look like that other periodic table, right? This looks a bit weird. This is all these different colors for each different element. So if I had a hot gas of each element and I took a spectrum of it, this is what I would see. I would see all these individual lines. Some of them, like iron, have loads of lines, and so it's actually difficult to see them apart. But like up here, hydrogen has one electron. And actually, these lines are all coming about from the electrons in the atom jumping around. You know, and if you go then to helium, you see that's a little bit more complicated. It's got a few more lines. So normally in stars, we see these as absorption lines. We see them as dark lines. So that's how we can work out what stars are made of. But here, because we've seen this stuff thrown off, we're looking at the emission spectrum, and we can work out what stuff is in those dying stars like our sun. And so what do we work out when we get that? Well, let's go back to the periodic table where we're looking at all the different elements and what they are. And this is what we get. So if we look in yellow, these are the elements that are produced by those dying low mass stars. So the hydrogen helium burning that I was talking about, the edge of the core, that produces actually most of the carbon and nitrogen in the universe, right? So a sun-like star had to die to make the carbon and nitrogen you need for your proteins in your blood. Thank you, star, wherever you are. Well, it's not there anymore. It'll be a white dwarf somewhere. Because broadly, you know, if those things get thrown out into the things, it doesn't just then go straight into other planets. It's got to be mixed up with other material. And so actually, this is like where stars are feeding into galaxies to form the next generation of stars. So that's where, you know, our star is a second or third generation star when it's had that many other types of stars, deaths, the material they produce mixed in with us. But then we also get all these heavier elements, you know, strontium, yttrium, zirconium, a little bit of gold, not too much, a little bit of silver. So, you know, but you do get these heavier elements. And that's by a different process where it's where all the complications come about, where you've got like some of the, you're adding on neutrons because to the elements, and you'll also keep on making heavier and heavier ones. And it's something called this S process. And S is for slow, right? Because these stars, as they're dying, take hundreds of thousands of years to die. That doesn't maybe sound like a long time, but that's quite quick. Timescales are a problem with stars because, you know, you can go from talking about billions of years being slow, but then you also talk about 100,000 years being slow. So yeah, I'll try not to confuse things. But anyway, we look at this, and so that's how these things happen. We actually start an ion, and what the star does, it keeps adding on neutrons onto things until they decay to the next element, and so it goes away. But the peaks in this S process are here with the strontium, yttrium, zirconium, and there's another one down here with the lanthanum, the neodymium. I cannot say all these elements correctly. And as well, you've got things like lead and bismuth, which are like the last stable elements. These grey ones, they're produced, but they don't last long enough to actually make it into the planet. They're decayed before they get there, except for if we go back, and I did just say, you know, so we're looking at the, for example, these emission spectra, right? But what about looking at the star itself before it died? Can we see these elements being produced in those AGB stars, those stars like our sun that have gone through its core hydrogen burning, form the helium core, and then form the CO core? Can we see elements being formed in them? And the answer is yes. So when I looked at this, the Burbage, Fowler and Hoyle paper a couple of years ago, oh, sorry, it's actually last year, I was really excited. I was just flipping through and I suddenly noticed for the first time that here it's actually got these technetium, TC lines. So this is actually part of the evidence they used in their work to realize, oh, hang on, nuclear reactions are going on in the stars. So this is actually the third piece of evidence So here, this is a spectrum of a red giant, very cool, big red star like our sun, producing technetium. And look, there's none on the Earth. Its half-life is too short. It's all vanished after 100,000 years. The only way that element can be in that star is if it's being made right now. So that's quite amazing. Okay. Should we go to the next element? Right. So we've got some of the elements of the periodic table, not a lot. You know, those heavy ones are useful, maybe. I mean, some of those really heavy ones are useful for the computer screens we're using right now. They're like all modern technology. They're the rare earths, which is great. But, you know, we've only got carbon and nitrogen. We have to hold our breath until we get to the next type of stellar explosion, right? Because we haven't got any oxygen yet. We haven't got any iron. Why do I talk about iron? So iron is really important because your blood is based around hemoglobin. Hemo means iron. And so you need to have iron and oxygen to be alive, right? Because you need to have oxygen to breathe, and then you need the iron to take the oxygen around your body so you can metabolize all the carbon compounds that have the sugars in there. It's really exciting stuff. I love this stuff. I love this story. So let's go and think about stars like our sun, but in binaries, right? So this dying low mass star is for single stars like our sun. Most stars are actually not like our sun. Most stars are actually in a binary star system. So that's a star where you've all seen Star Wars, the binary sunset at the beginning, right? That's the kind of thing we're talking about. Two suns orbiting around each other. I mean, you could imagine that the Earth-Moon system is a bit like a binary planet, some people consider it, because you've got the Earth and the Moon orbiting around each other. But imagine there were two stars. The brightest star in the night sky, Sirius A and B, is like this. Now, the reason I wanted to talk about this one is we talked about how the sun will produce a white dwarf at the end of its lifetime. If that's in a binary system, the more massive star will evolve quicker. The more massive a star it is, the more quickly it burns through its fuel. And so here you've got Sirius B and Sirius A, right? A is brighter than B, which is why they split it up that way. But initially, Sirius B would have been the more massive, brighter star because it's the one that's now died to a white dwarf. You know, and Sirius B is now a sun-like star. It's about twice the mass of the sun, so it's a little bit brighter, and they orbit around each other. So I'm just going to describe now two interesting ways that this can now produce other elements, right? So this is my sketch. I got a new tablet and you can draw little things. So I've been experimenting with different ways of drawing diagrams. And so if we start here with two stars orbiting around each other, right, main sequence stars like our sun, the one that's more massive will get bigger. And it will do one of two things. Either it will suddenly grow to a point where material, the gravity of the other star pulls material off and forms a little disk around, forms a little disk around it. Okay. Or you'll get something called a common envelope phase, where actually the other star, the more massive star, gets so big it engulfs the other star and it goes through really weird stuff. The result will eventually be the same. Well, okay, with common envelope evolution, it may end up merging and just becoming one star, so we can ignore it because it goes back as we've just described. But sometimes you end up with the helium core being exposed and basically it becomes a white dwarf early. So you don't necessarily get all the elements you just talked about being produced. But then you have the other star that's still a main sequence star. The white dwarf gets smaller because it's got no more nuclear fusion. So it just dies away and just sits there for the rest of the age of the universe until the other star, that's still a main sequence star, that tries to become a red giant, tries to grow, and then the white dwarf steals material from it. Now, if it transfers material at just the right rate, and it gets to a mass about 1.4 times the mass of the sun, that is, the white dwarf gets to that mass, it can't support it. If you look at the quantum mechanics and the way the star is held up by something called electron degeneracy pressure, it just collapses when it gets to about 1.4 times the mass of the sun and it explodes. So what happens when you have like 1.5 times the mass of the sun, all made of carbon and oxygen, and you explode it? Well, it burns very, very reactively. And so there it can produce many more elements. And actually it burns so much, it disrupts the entire star and ejects it. The one other complication from this I'll just mention is that you may also have heard that sometimes after that mass transfer, you actually you form two white dwarfs, and those two white dwarfs can merge. And again, if those two white dwarfs, when they merge, are greater than that 1.4 mass that explodes. Just to try and point out that while I can always talk about one model, there's always going to be complications. You might have read something somewhere or read something somewhere in the future to go like, but hang on, what did Jan say? You know, so I'm trying to give you a simple applied picture, but yes, it's always this case that these white dwarfs that are coming from stars like our sun in binaries have two ways of exploding if they get to this mass limit. And they look quite pretty when they blow up. Here's this classic image of a Type 1a supernova. It's a thermonuclear explosion, Type 1a supernova, because it's all this carbon-oxygen white dwarf that's just exploding. And it's this one down here, right? And you can actually see it's quite far away from the disk of a galaxy. So it is much further down here. So where do these elements come from? So if we've got dying low mass stars and exploding white dwarfs, it's these blue ones. So it's solar-like stars in binaries produce these other elements. So actually they don't produce many, but they do produce ones that are important for life. So like iron, nickel, copper. I say copper is important for life because there's some crabs that don't have hemoglobin, they have the copper equivalent. So again, all life really needs these elements that are being produced by these exploding white dwarfs to be able to take the oxygen around your blood. Right, so that's cool, but we can already see a picture where it's actually funny when we're looking at these elements, we need to worry about the single stars and the binaries as well. And so that's where we're going to go with the next one in the last 10, 15 minutes in a second, to talk about what are the massive, so how do we get the other elements? And you can guess that one of them is going to come from the single stars, exploding in a different way, and the other ones will be coming from the binaries. Right, so what about oxygen? All we need is the air that we breathe. Great song. Whoever sings it, there's many people who have covered it. So if we go to a more massive star, stars like our sun, unfortunately, I have to say this are boring because they're low mass stars. And I grew up doing my PhD in massive stars. Why are massive stars so much better? Well, because if they're more massive, there's more pressure, there's more mass pushing down at the center, and so the center can get to higher temperatures. And so stars like our sun will get to this carbon-oxygen core and stop. They'll become carbon-oxygen white dwarfs. Stars over 8 times the mass of the sun or so can go further. They can get hot enough in the center that you start burning carbon to oxygen neon, and then the neon to oxygen magnesium, then the oxygen to silicon, and then actually it keeps on going until you form this iron group elements core of iron, nickel, and cobalt. And if you look at the energy released by nuclear fusion, once you get to iron, that's the most stable element in the universe. And you can't get any more energy out. And actually, you get 90% of the energy going from hydrogen to iron just by going from hydrogen to helium. So stars spend 90% of their lifetime burning hydrogen to helium, and all of the other elements only give you 10% of their lifetime. But we get to this iron core, and it can't produce any more energy, so it collapses down. It doesn't explode because there's no more energy source. And so what actually happens, it becomes a neutron star, or possibly a black hole. But then again, this is a problem because I'm telling you about all these exciting nuclear reactions that are going on in the core of the star. But again, I'm saying, oh, like before it got locked away in the white dwarf, unless it was a binary neutron star binary explosion. Here, all the elements up to iron are being locked away inside the neutron star or the black hole at the center of the star. And what actually happens is when you take your iron core, which is about the size of the Earth, it's about the mass of the sun, so its surface gravity is something like 330,000 times greater than on the planet you're sitting now. It collapses down, releases about the same energy as the sun will emit over its entire 10 billion year lifetime in a few seconds. And so as my really complicated simulation will now show, it explodes. Okay, it goes bang. So it lets the neutron star, everything explodes. Let's actually look at some real supernovae, which are much more interesting. So you can see here, these are two Hubble Space Telescope images on the left and the right from a 2.5 meter telescope. The one in the center is from the VLT. It's an 8 meter telescope. And so you can actually see here, this is why astronomers go to governments to say, give us lots of billions of dollars to go and build big telescopes because, we can see things in greater detail. But this cool fuzzy red blob here is aligned with this stellar explosion here. And if we go back a few years after it exploded, we can see that that star has snuffed it. It has shuffled off its mortal coil. It's an X star. The great thing, I'm assuming there's probably some older people here who know about Monty Pythons, so I can make that joke, right? It's like the parrot sketch, right? It's an X. Anyway, yeah. But we see this in nature, so I don't need to do a simulation. I can link with what my models, and my PhD was basically trying to make computer models of this to see, can we predict where these stars explode? And the answer is we do. So we actually really do understand stellar astrophysics, and we see like thousands of these type of supernovae. And you can see here, these are the Supernovian Galaxy M51, I think. I always get this one confused with M52. I can't remember. But these are actually happening in a very different place. You can actually see there's lots of blue stars here, which shows you it's happening where the young stars are exploding. So whereas yeah, I'm trying to think. Anyway, yeah. So we see lots of supernovae, and these are again. So the previous supernovae, those exploding white dwarfs, are type 1a thermonuclear supernovae. These are called core collapse supernovae because the energy is released from the core collapsing down to a neutron star or black hole, and they come from younger stars. And we see many type of different things. These are all X-ray images, actually, of supernovae. Some of them are type 1a, but these ones have neutron stars at the center. And so again, you've seen these elements locked away, but no, you've also got the ejector around the supernova. And so actually by studying that stuff that's been thrown off in a similar way to those planetary nebulae, but it's all different time scales, we can actually work out what these elements, and we can also get this from models, what they should be producing. And so we can go back to our periodic table and we can see that we have oxygen, which is really good. It's all these green ones, right? So actually, even though a lot of the oxygen has gone in that was formed during the lifetime of the star, it's gone into the central black hole or neutron star, you get all these other elements by explosive burning. But because it's a different type of explosion, right? It's not a white dwarf exploding, it's this massive star exploding and you're around the neutron star black hole at the center, you get different elements. And you go pretty high, you go up to, I think that's rubidium, but you don't go much further. And of course, this doesn't tell you about the relative abundance of each individual one, which is also a key thing we use to try and understand what's going on in the stars. But yeah, so all the air you breathe has basically come from some massive star exploding. That's quite exciting. So, if you ever feel boring just sitting there breathing, you can just think like, I think I'll sniff some supernova debris. Yeah, feels good. Yeah, although the air is mostly nitrogen, so it's mostly come from a dead sun-like star. Okay. I'm glad somebody has got mine. I normally lecture to like 20-year-olds. So you try and come up with a Monty Python quote and it's just like, they don't get it anymore. But I'm trying to watch things like Paw Patrol with my daughter and all the young, all the current like shows, because like in 10, 20 years time, when I'm lecturing those students, it will like pay off because I'll be able to make those jokes. Okay, you got to plan long term if you're an astronomer. Okay, right. So where are we? So let's do a reverse of what I've just said. Well, the same thing. Okay, I talked about the evolution of a single star, how it makes some elements and then exploding white dwarfs. We've talked about the exploding single stars. And actually, even if those massive stars are in binaries, they still explode and they still produce these elements. Nothing really changes. But there must be one other little key to this story that I'm going to go on about now. And that's back to binary stars and gold. So it's really nice that when you talk about low mass stars in binaries, it's kind of, the evolution is kind of simple, right? Because you don't have to worry about the star exploding until the very end. The problem with massive stars in binaries are it's still the same thing. You still get two main sequence stars. The more massive one interacts and dumps material or interacts with the other one in some way. You still get a helium star. It's not a white dwarf. It's too big. It's going to go through further nuclear burning stages. It's going to get up the iron core because it's a massive star. It's like already still at least 5 times the mass of the sun. And it's still got this other main sequence star. So this star blows up. Different type of supernova, but you still get a lot of the elements produced. Now, because that's explosive, most of the time, the neutron star and the black hole and the other star that was orbiting around it actually normally fly apart. But in about a few percent, they actually stay bound. And we see many, many systems where you've got a black hole or a neutron star orbiting around a normal star. And actually, in a few years' time, we're going to detect thousands of these because of some of the new surveys that are going on in the night sky at the moment. But now what's interesting is that then you have this main sequence star that will evolve and grow. And actually then it will dump material onto the black hole or neutron star or swallow it. And actually, so that neutron star and black hole may grow a little bit. And actually these disks and everything is so hot that these produce X-rays. And actually with these see X-ray binaries where you have a neutron star or black hole accreting material from a stellar companion. But again, eventually you'll have a helium star and that black hole, which will again explode. And again, depending on things, it's very more likely they unbind, but sometimes they stay bound together and you get 2 neutron stars or 2 black holes or a neutron star and a black hole orbiting around each other. Okay, so if they're black holes, that's really boring because black holes stay like that. They're just like holes in space-time and they'll merge together and maybe become a more massive black hole, but all the elements, you can't get anything out of them. But if they're neutron stars, then we have something new that we can happen because there's stuff there, right? So if neutron stars, they can slowly merge over time. But why? Because what's going to cause them to merge? And the fact is that neutron stars and black holes are extremely dense objects. And the fact is that space-time is weird. Now I say space-time because this is also something complicated. It's based on general relativity, which is where our concepts of space and time are really complicated, right? And you can have an entire series of lectures, right? Every university physics course has a course on special relativity and then general relativity because they're so complicated. But it means space-time is curved. And one of the interesting things is the picture we have is if we have two neutron stars or black holes, as they orbit around each other, they're kind of warping space-time. That warping is moving. And so actually, like you have like two things moving around, for example, in a water, you'd see ripples coming a lot away. There's ripples in space-time. Space-time is, of course, much more stiff than water, and so it's very difficult to detect, which is why you need black holes or neutron stars to do it. But these waves take away energy, and so the two objects spiral in together and get closer and closer, and actually the closer they get, the faster they go. We've now been able to detect this, and we now have something like 50 events, over 50, actually must be closer to 100, but they haven't released the latest catalog of all the neutron stars and black holes that have merged and been detected by this gravitational radiation, or gravitational wave radiation. It's not easy to do it. Here are the two images of two gravitational wave observatories. You need to have 2 kilometers that are about two arms that are 4 kilometers long, different right angles. You make them vacuum, you shine lasers, bounce them down on something like 100,000 times, measuring the distance of those arms to see how space-time is warping. You put one in a swamp, so there's lots of crocodiles around to keep people away, and the other one is near a nuclear waste dump, again, to keep people away, because people are the noise, right? The signals we're trying to pick up are at the frequencies of hertz. And like, you know, there's an awful lot of things that humans do at the frequency of a few hertz. So I'm not going to talk about the black holes because they're exciting in their own way, but let's talk about the neutron stars. And so this is the first neutron star merger that was seen by the LIGO, which is the Laser Interferometer Gravitational Observatory, where they've detected 2 neutron stars spiraling in together in their final death throes. And you can see the frequency of the signal is somewhere between 50 to 500 hertz. And if you were to listen to this, it would sound something like a whoop. And we actually call it a chirp because it's like it increases in frequency and in amplitude as it gets closer. And yeah, so we didn't actually detect the merging. The future upgraded version of the observatories will be able to. But yeah, so this is great because we detected this by gravitational waves. And you know, if that was all we had done, then we would have this picture. We have this picture of these 2 neutron stars burning together, forming a black hole somewhere in the center here, and that neutron material forming a disk, throwing out some material, and you've got 2 jets, you know, and you know, this would all be conjecture until I can show you the picture of the afterglow of that event. So this was the best studied object ever in pretty much the history of the universe. It's something like, I think somewhere between, I think it's about 1/3 of the astronomers in the universe knew, sorry, on the Earth, at least, I should say, 1/3 of the astronomers on the Earth knew about this event. The other 2/3 knew about it, but weren't meant to know about it, right? Because you can't keep something this big, this impressive secret. Especially when the Hubble Space Telescope tweeted, looking at binary neutron star merger, because, you know, it tweets about everything the Hubble Space Telescope looks at, and someone had triggered the alert to look at this galaxy, forgetting to ask NASA not to tweet about it. Anyway. And this galaxy it happened in, it's quite funny. If you look at, it's NGC 4993, if you look at the Google statistics of how many people Googled this galaxy, maybe basically no one Googled it. And then a few days after the merger, suddenly you can see the number of Googlings just shooting off because everyone's trying to find out about this galaxy because it's really boring. It's an elliptical galaxy. It's about, I think if I remember correctly, about 40 megaparsecs away, which is about 120 million light years away. It's like billions of years old. I have a postdoc at the moment who's trying to understand it. So when people looked at this galaxy, they wanted to understand the age of it, which you do by looking at the stars within it, but they assumed all the stars were single, right? If this binary neutron star merger came from a binary star, you know there's other binary stars in there. So we're trying to work out what the age is with binary models, which is what we do. And we're actually getting a slightly different answer. So it's really interesting what we're doing, and we're hoping to try and publish this soon. But here is this galaxy, and here is the afterglow of 2 neutron stars smashing together. You know, and you can see that it's actually fading very quickly. But then it became brighter and brighter. So this has been studied in every single wave band, and it's really amazing that they found it so quickly. That, you know, there were so many wonderful things because the data was so amazing. But what's actually happened in this is you've had a neutron star. Now, I didn't describe what a neutron star is. A neutron star is a big ball of neutrons. What happens if you take your elements and you keep on adding on neutrons? Eventually, you get to a ball that's just full of neutrons, and that can actually hold itself together, and it's a neutron star. Now, what happens when you destroy a neutron star is here when you smash two of them into each other. Well, you form a black hole, but then also you throw off lots of material. And that material is basically neutron star material. Neutrons don't like being in a lighter mass thing. They actually decay. Even if you had a free neutron, it would decay to being a proton in about 8.5 minutes. I think, roughly. I can't remember. That might be, it's something about that. So you actually form here lots of really heavy different types of elements, and it's something called the R process, the rapid process, because you've got lots of neutrons in a very short time scale, comparing that to the S process, slow process I talked about earlier on. And so that's where this glowing is coming from, because you've got these blobs of neutrons that are decaying down to protons, and so they're producing lots. So this would not be a nice place to live, right? So that's one concept to come on, but also there may be a reason to actually go there, because if you look at the elements that are being produced, they're the orange ones. And so, you know, people think and do some calculations, and there may have been something. If you look at the spectrum of the event as well, we know an awful lot of gold and other heavy elements were produced there. So while it may be really nasty, and you know, you'd probably get fried by all the radioactivity if you went close to it, there might be a Jupiter's mass of gold there and all these other rare elements. So, you know, it's interesting. If you look in science fiction, you can see people talk about gold planets. Like there's the classic line in Hitchhiker's Guide to the Galaxy, and there's another one in Doctor Who, the planet Voga, that are gold planets. Maybe they were formed around these exploding neutron stars. Who can say? But it's kind of exciting to think that. Yes, timey-wimey, wibbly-wobbly. Thank you. Okay, so I just want to end up. So we have different types of stellar evolution. We have different ways of making the elements. They come from different processes. We need high mass stars, low mass stars, but we also need single stars and binaries. But can we actually see through the history of the universe how these things have changed? You know, one of the things is low mass stars take billions of years to evolve. So the elements here, like iron and the carbon nitrogen, would have taken billions of years to be produced, whereas the oxygen coming from the massive stars would be produced quite quickly. So it's quite abundant. Whereas emerging neutron stars take a lot longer, and so that's actually probably why gold, silver, and platinum are so rare. It's just to do with the different time scales. So we can actually see how the composition. So this is the last thing I'm going to talk about, and I've talked about a lot of things. It's getting close to time. So if we look at how the composition of the universe has changed with time, you know, and so we think about this universe, right? So we think all the way back here at the Big Bang, just hydrogen and helium. Then we had stars. So because what would be the stars dying and producing energy first, it would be the massive stars producing oxygen. So the early universe would be very oxygen rich, but things like iron would only be produced about like midway through the history of the universe, and gold and silver and other heavier elements would only become much more abundant recently. So I'm going to show you now some complicated plots. Okay, I'm showing them just to try and I want to say for fun. It's not really for fun, but just to give you an idea of then there is evidence and things we do to try and show how this all works. Let's move that out of the way. Let's put down there. Okay. So here we have plots, and there's lots of data points here, and there's lots of models. And this is great work by Chikai Kobayashi, Amanda Caracas, and Maria Lugaro. And along the x-axis in each panel is the iron abundance. So on the left of each one, that's when you've got very little iron, so very early in the universe. And on the right, you've got very metal-rich material. And in fact, this one is actually the sun. So the center on the right of each diagram, that's where the sun is in terms of the amount of iron in each element, right? So each panel has a different letter, C and O. So let's concentrate on oxygen. Because if we go down in metal abundance, so earlier in the universe, we can see that the oxygen abundance is greater. And so actually, if we would go back to some of the oldest stars, which are right over here, where they've got very little iron, they had much more oxygen relative to iron, because oxygen comes from the massive stars that are produced much more quickly. And then actually you can see that there was obviously a change where the abundance of the sun was about 1/10 of what it is. The abundance of iron in whatever stars was about 1/10 of that. And then it started, obviously, this is the kind of, the delay time to when then the type 1a supernovae could start producing iron. Right? Which is one story to tell, because you look at all these plots and you can see there's a mess. There's all these different lines. The story is incredibly complicated, but it's wonderful to try and piece this all together, to try and work out how it all comes together to give us the elements we see, right? But it tells us something about the universe. Did we have to get to a certain iron abundance for planets to exist? That's kind of fun. And just to show you how complicated it can get, we've got all the elements here. Hang on, where are we? Next one. And so it can get hideous, right? But I don't get confused in the details. It's just so many. Anyway, okay. So to finish off, hopefully not having overrun too much. I'm sure I get told off. I'm just going to point out that in that original paper where all this is written down, it shows you even back 64 years ago, astronomers had a sense of humor, because they pointed out it is the stars above us govern our conditions. The reasons we have the chemistry we have is because the stars made them in those different elements, right? Carbon and nitrogen are so abundant, which is why it's there. And oxygen is very abundant too, which is why it can breathe it. But also perhaps the fault, dear Brutus, is not in our stars, but in ourselves, which is also kind of, yeah, the humans do kind of muck things up. Anyway, I'll leave you with my final slide, which is just to show that, this is a new way to look at the universe. We look at these things and you can see here galaxies which are close by because they look like galaxies, but every point of light in this, the very, very, very distant galaxies. And we're getting to the point now that whereas before those plots were individual stars in our galaxy, we're now trying to look at those very distant galaxies, look at the elements actually being made in them to try and close that loop and understand how the universe has evolved over time. So I hope that was really, really interesting. And I'm sure you've all got many, many questions. But yeah, so thank you for listening. And yes, I hope you have a good afternoon or an evening wherever you are. Thank you.
Thank you very much. That was an amazing talk. I learned so much, and I'm really excited for some of these questions and answers. Just a reminder to everybody: if you have a question, please don't hesitate to put that in the Q&A section, and we will ask them live. First of all, let's start off. It looks like there's kind of a couple questions that relate to each other. One is, how many star life cycles have happened before the creation of our solar system? And the side question with it is, can you estimate the number of generations since the Big Bang?
Okay, I'll stop my slides. I'll stop sharing my slides, but I can always go back if I need to. That's a really interesting question because it's like just I would say it's a slowly happening car crash, right? Because there's a problem with this. The stars have different lifetimes. So if you go to the most massive star, it will have a lifetime of about 3 million years. The longest lived, so there's actually some stars that could have been born in the first generation and are still not died. So the lowest mass stars have lifetimes of 1,000 trillion years. And the universe is only 13.8 billion years old. So it's like, so there's definitely many generations of the massive stars, because, if you take 13 billion divided by 3 million, that's thousands. But if you look at stars like our sun that are 10 million years old, there's maybe only one generation of stars that could have gone through their lifetime before it was formed 4.5 billion years ago. So it's a mixture, and it's always a mixture of different elements that come together, which is part of the story of trying to understand what our sun's composition is. So there's some great fun stuff you can do. So you can go to meteorites, and within some meteorites, you can actually see individual grains that have come from individual different types of stars. And you can see that they've come from different stars. And so you can try and piece together, how many of these type of stars of this mass, of this composition, had to produce this stuff. So it's a wonderfully complicated question. And one of the other things to think about more broadly is, while I've been talking about the stars, if you think about a galaxy and how within that galaxy, all these different stars are producing stuff and it's all being mixed around. And so it's like it's a constantly moving cycle. But if you wanted a number on generations, I can say that there are what we term 3 populations of stars that astronomers use. And actually, this actually comes from studying the galaxy rather than stars. And so there are population 1 stars like our sun that are quite young, 4.5 billion years young, right? But they're metal rich. So they've got about 2% of their stuff is everything that's not hydrogen and helium. You've got population 2 stars, which are older, and they're a fraction, like maybe a fifth or a half something of the metallicity of our sun, so maybe 1 or 0.5% of metals. And so they're much older because all their massive ones have died. But then also you've got population 3 stars, which are the first stars to form, which had no metals. And as with anything to do with astronomers, we name them population 1, 2, and 3 and get them back to front, which is great because we always get things wrong. That's a really good question. Thank you.
Awesome. So in the periodic table of the elements with the spectrum, how come the absorption isn't showing, but the emission is? Is it just kind of just standard, or?
Yeah, so it's a standard way of doing it. So there is absorption. They happen in different places. So if you want to look at an element on its own, it's very easy to make an emission nebula or an emission spectrum because you just make it hot. But if you have that same gas in front of a hot body that's producing a Planck spectrum or a continuous spectrum, right? Because so if you look at the sun, don't look at the sun. It's bad for your eyesight. I should always say that, right? If you look at the sun, especially through a telescope, it'll make you go blind. Please don't look at the sun. Health and safety is important. It's got wavelength. It's producing light at all wavelengths with a peak in the green part of the spectrum, but it's producing blue and red. But if you look at it very, very in greater detail, you will see dark lines of absorption spectrum because there's elements in the atmosphere that are absorbing those light rays. And so we see them as absorption lines because you've got stuff in front of a continuous spectrum. Whereas if you've just got that stuff in a hot, cold gas, that's when you get the emission spectrum. So actually the spectrum behind Simon, is that the Pleiades though, or not? Or is it, do you know what star cluster is behind you?
I can look it up. I don't remember. I knew about an hour ago, but now I forgot.
Well,
so many great things in the universe.
In star forming complexes like that, that's a good example of an emission spectrum because you've got the gas near the stars, and so the stars actually heat up that gas and it emits at the emission lines, just like things if you have fluorescent lights, because so many people have LED lights now. It used to be that everyone would have a fluorescent light bulb. You know, there you have the gas that's emitting because the electrons are jiggling around, you get an emission spectra. And so it's the same lines, but the emitting regions are different. And so we always put them in emission because it's easier to see the colors rather than to see the absence of the colors. And hydrogen would be really boring because it would just be everything.
Yeah.
Yeah. But if you look at star forming regions, they look red because they're mostly hydrogen, and hydrogen has this really strong H alpha line feature, which is red. So that's why you always see in a lot of images of galaxies, you see the red star forming regions.
Mm-hmm. Can we calculate how much of each element can be produced from a certain source? Say exploding of neutron star A with a known weight?
Yes, but it's really complicated. So there's two aspects to that question. And I want to say it's really I want to say yes, we can, right? Because we do, obviously. We make models and its entire cottage industry and all those different elements in the supernovae, in the low mass stars like our sun, in the type 1a supernovae, in the emerging neutron stars. People can sit down and make those calculations and make it predictions. And actually the final slides I showed where people had those models, those lines that were combined against the measurements of abundances in stars, that's where they was trying to bring together all those different predictions for how much elements are made, along with a model of a galaxy to see if they can reproduce the abundance of stars we see in our galaxy. And they can, although it's uncertain because it's not just each event and how much stuff you produce each an event. For some of them, like the binary neutron star merger rate, we don't know that. It could be 30, it could be 1,000 per cubic gigaparsec per year. We just don't know, and that's a big difference. So it's really complicated, but we're getting to the point that within the next decade, we'll have all these observations that will be able to tighten those numbers down. And with binary neutron stars, so actually with this R process, we always used to think it was actually core-collapsed supernovae that produced those elements. But when we looked at it, we didn't see enough being made in those supernovae. And so now we've discovered them being made in these binary neutron stars, and we know that they actually exist and occur in the universe. It's like, okay, well, that tells us where all the gold comes, well, a lot of the gold comes from. Just to go on to this thing about neutron stars are really weird objects. And, stars are pretty easy to understand. I say pretty easy to understand. They're still really difficult, right? Because at the center of stars before they explode, the densities are something like 10 billion times that of water at the center. The temperatures are 10 billion Kelvin. So quite hot, quite dense, really extreme. But that's easy to try and understand compared to neutron stars, because neutron stars are basically at nuclear densities. So it's something like 100 billion times, no, hang on. I need to get the calculation right. 1,000,000 billion times denser than water in a neutron star. Neutron stars are so extreme that on the surface gravity, when you look at it, if it's a sphere, you can see behind the equator because the light rays try and come out directly off the surface, but get bent round by the gravity. So you can see something like 60 to 80% of the surface by looking at one side of a neutron star.
Wow.
And we have models called nuclear pasta models about what go. We really don't know what's going on. It's really annoying. But interestingly, it's the gravitational wave observations that will be able to help us understand how dense and what that material looks like. So actually, when they hit, we know what their radii is, and then we'll be able to start making much better calculations about what actually happens when those two things merge, because we'll know what nuclear matter at those densities happens with. And we'll be able to make much more accurate calculations. It's really wonderful, exciting stuff. It's another reason to do astronomy, because people sometimes say, why do we want to know what's going on at the very? I mean, it's always there's blue skies research, which is really important, and we can go and build particle accelerators like the LHC and CERN. But in the universe, you have these extreme events, which we could never do that in I should never say never. It's very difficult to make in a laboratory, right? So millennia away from ever being able to do that in a laboratory, but we can watch these events in reality. Let nature do that for us, and we can understand the physics, and it makes things easy to understand generally. That was a long answer.
Well, that's great. Thank you so much for that answer. We have a few more questions here. We have a question that asks, based on the graphs that you showed, is there a period in the history of the universe where there was a peak creation of most elements? It looks like many of the elements you showed seem to peak around the same time. If so, what are the implications of that for future stars?
Yeah, so it's not so much the peak. I think there was that thing with the oxygen where it suddenly bends. So I think that's basically the difference between when only massive stars were exploding to produce oxygen, and then the type 1a supernovae, which come from those exploding white dwarfs, started, and you got more iron. So it wasn't. So it's like you're adding in oxygen, and then suddenly you're adding in iron. So the gradient of that slope changes, and that would probably be somewhere around about. In theory, that's about after 50 million years of the first stars forming, depending on many things, because we've never seen the first stars to form. We may do within the next century. I'm going to guess it may be sooner or later. I don't know. But they may have been very different. So actually, we may not have had any of the low mass stars that would produce those type 1a supernovae until much later. But let's say somewhere between 100 million and a billion years is where that change in the average composition would have started. We do know, if we look back in history, because this is something we're really looking at with my own group, is if you want to predict the number of these neutron star mergers and black hole mergers, you need to understand how many stars are formed in the past. Because if it takes billions of years for something to occur, you've got to know not how many stars are being formed today, you've got to know how many stars are being formed a billion or 10 billion years ago. So the peak in the star formation rate of the universe was, I think, around about, I want to say about 10 billion years ago. And we can see that quite clearly. Because we know that when the universe was formed, obviously there was no stars, and then you started forming more and more stars because you just had more gas collapsing down, and then the turnover is actually to do with the fact the universe is expanding, and because the universe is expanding, the star formation and there's still the same amount of stuff. So if your volume gets bigger for the same amount of stuff, then you've got fewer stars being formed, and when you do this calculation, the really depressing thought is something like 90 to 95% of all the stars that will ever form in the universe have already formed. So there's only like a few percent of stars. I mean, there'll still be, it's actually the number is quite high, but it's like downhill from here on in, right? So it's interesting when you look on the very long time scales of predicting what's going to happen in the future of the universe, where would be the best place to actually live? It's around those very low mass stars that have the 1,000 trillion year lifetimes. So yeah, can somebody ask a more interesting, upbeat question? Because I've just told you how it's all gonna happen.
Yeah, exactly. We have a question that asks, do we have models for how the heavy elements got into the Earth? Some of the rarest elements, the radioactive ones, are crucial to making the Earth the dynamic world it is with a hot core. But how did we acquire those rare elements? Were some special conditions needed in the original solar nebula?
No, it's happening all the time. And actually, we see in different stars that they all got different compositions. So yeah, so again, you can think about this galaxy as if you have a box. you can actually model it as a box, and you've got stars in it that are producing elements, but there's gas in there. And so those elements stars will produce will go into the gas cloud, which will then become the next stars. So there's actually a cycle. And this is how people make those plots I showed right at the end. It's how they make those models. They assume the galaxy is effectively a box. Stars are going in, and the new stars and planets around those stars are being made with the material from that gas. And so it's just because basically you've mixed all the different stuff being produced together. Maybe a supernova went off nearby, produced a bit more elements, mixed with all the other elements, and that collapsed down to a solar nebula. So it's just because that's the average composition of what you'd expect in the galaxy, which is where we come about. So that's one, I mean, you can use the average, the relative abundances of elements within the Earth and the solar system to try and work out how many supernovae or how many dying low mass stars we needed of different types to get to those elements. Now, there is a complication in this. For example, behind me, I have Jupiter. Jupiter is mostly hydrogen and helium. There's not a lot of hydrogen and helium around us. The Earth is mainly, as you say, made of the heavy elements, oxygen, iron. And that's because planet formation is, again, an extra layer of complication on trying to understand where the elements come from, because all the elements went into the sun. But then when the planets started forming, it depended on the temperature, how close they were to the sun, which elements went into the planets. So for the planets we got, both the terrestrial planets, you get mostly oxygen, iron, silicon. Oxygen, I think, is the most abundant element in the Earth's crust, then silicon, then iron. Whereas the outermost gas giants were a lot colder, and so they could actually hold on to the hydrogen, which is why they're so hydrogen rich. And so there's that extra complication that also depends where you are in the solar system as to what your composition is. And then if you look at the composition of the planets, there's other things that happened in the solar system formation that, you know, if you look at Mercury compared to Earth, Mercury is almost basically all iron. So something has taken away all the light elements. But then the final complication I get on, so we can go on to the next question, is that if a planet gets big enough, you get differentiation. So everything melts, and that's where the heavy elements sink down. So the core is an iron, nickel, cobalt core, but then the silicon, the oxygen, which is much lighter, float up to the top, which is why we've got rocky surfaces. So, you know, it's one of these things with all science, when you look at something and you're trying to understand it, you've got to understand, you know, is the composition of the sun really going to be like the surface of the Earth, like we used to think? And actually, when we go back to Celia Payne-Gaposchkin, if you look at her first PhD thesis, which is where she says, oh, the sun is made of hydrogen, no one believed her because they didn't believe that the sun could be made of anything different to what's lying around us here. And it was funny because then one of her examiners a few years later said, oh no, she's right. And he got credit for a few years. But now it's everyone knows that because Celia Payne-Gaposchkin actually had to say in a thesis that it was hydrogen. It was quite exciting. So yeah, sorry, another long answer. But there's lots of different complications. It's cool. It's good fun.
Yeah, we got a bunch of questions coming in. Are the three generations of stars relatively homogeneously mixed in all parts of the universe, or are there clumps of older stars together and clumps of younger stars together?
Yes, so this is interesting. So with population 3 stars, we haven't seen any. So there may still be a few lying around, but they've been camouflaged. They've got dirty because they've been around for 13 billion years. They may have accreted a little bit of material, so we might not recognize them as such. Within our galaxy, I mean, so actually when you look at galaxies, there are some galaxies that have got only low metallicity young stars or population 2 stars. So for example, the SMC and the LMC, the Large and the Small Magellanic Clouds, are 2 satellite galaxies around our Milky Way. They're basically all those low metallicity stars. Whereas if you look in our galaxy, because it's a bit older and a bit bigger, we can actually see that towards the galactic center, and there's a bulge, and there's even a halo around our entire galaxy made of the population 2 very old low metallicity stars. And then there's a thin disk, and in the thin disk, there's the population 2 stars. But of course, you know, you can still find population 1 stars in the disk because they're like passing through. And it's just the population 2 stars that are really young ones, and it's disk in our galaxy that has the gas, and that's where they're made. There are exceptions to that, but that's in general the rule. So you can see them in different structures, but that you can use them to understand something about the history of the galaxy and how it formed by where the population of galaxies are, which is a really good question. So thank you for asking that.
Based on the amount of rare elements in Earth's crust, can an estimate be made on the number and types of supernovae that occurred in our region to provide the elements during Earth's formation?
I'm going to say yes, it'll be tricky, and someone's probably done it. I mean, so there is one really cool thing. that geologists have looked at sediment on the seafloor, and there is a layer of, I think, iron 54 or something, and we know that that probably came from a supernova, and so we know that there is at least one supernova that happened near enough a few million years ago that the ejecta is actually recorded in the sedimentary layer on our planet, which is really quite exciting.
Wow, that is really cool. I know that'll be fun for the geologists in the crowd. Somebody asks about quark stars. Do they behave differently from neutron stars in the production of heavy elements?
Yeah, so this goes back to the fact is we really don't know what's going on, unfortunately. And so people have said, so if white dwarfs, right? So white dwarfs and neutron stars are similar in the way that they're both held up by something called degeneracy pressure, where you can't put two particles in the same space. So white dwarfs are held up by electron degeneracy pressure, so you can't put two electrons in the same space. But that's quite far actually. If you look at how small atoms are, that means it's basically your atoms are touching as close as they can do. For neutron stars, it's where you can't put two neutron stars in the same space. And so there you're going from something the size of atoms to something the size of nucleons, which are 100,000 times smaller. So neutron stars can be much, much smaller. Now, a quark star would be the next logical step beyond a neutron star, which is where you've actually gone between the neutrons, because inside a neutron or a proton, there are three quarks, which are three subatomic particles. You can never actually get a quark out on its own because they're being stuck towards a strong force. And the really cool thing is why neutrons and protons stick together is because it's the gluons that stick the quarks together are leaking out of the neutrons and protons and sticking different neutrons and protons together. Yeah, I love physics because there's all these different layers when you go into it. But anyway, so if neutrons have quarks, maybe you could go through and put your quarks together. We don't know, because we don't know what actually goes on, because the conditions are so extreme. We don't have the physics yet to understand it. Measuring the radii of neutron stars will give us a handle on what it is. And maybe neutron stars actually are quark stars. If you go right down into the core, maybe there's a quark gluon plasma. So yeah, and in case you're wondering why they're called quarks, is well, we just run out of names for them. So quarks are the bits inside, and they're stuck together by gluons. Oh, it's wonderful.
Perfect. I've got a fun question for you. I think it may have been alluded to in an episode of Doctor Who, but which has a greater force between a black hole pulling inwards or a supernova explosion outwards?
Depends where you're standing, right? So there's one interesting misconception about black holes, which is everyone assumes they just suck stuff in. But if you're orbiting around a black hole, you're not suddenly going to get sucked in, right? It's only if you're stationary you're going to get sucked in. But if you're how do you form a black hole? So you normally form a black hole in a supernova, so that core collapses down. If it's massive enough, you actually get a black hole. But then you still get a supernova, although this actually is current research, and different people would disagree with me because we're not too sure what really goes on. We're not too sure when we do get a black hole or a neutron star. We're getting there. But we're pretty sure that, if you're really close to the black hole, of course you're going to end up inside it. But if you're further enough away, you'll get exploded out and you'll fly away. But then some people say that maybe if you form a massive enough black hole, you don't get a supernova, you just go. So and there is one star we think where we may have seen this happen, where the star may just be going, or you formed a black hole, no explosion, and slowly the rest of the envelope is just filling down onto the black hole. So even though that's a bit fun, I don't know if it's been in Doctor Who, but we really don't know.
Wow, that's great. Thank you for that answer. Somebody asks, are meteorites able to contribute to this research?
Yes. So when I was a PhD student in Cambridge, it was Maria Lugaro, and I didn't know about this until she started talking about it. But meteorites are pristine material, right? If you get the right type of meteorite, as I said, you can still see something called a pre-solar grain. So these are dust particles, because when you look at so again going back to the image behind Simon, you can actually see dust here as well, dark patches, and it's like about the same size as cigarette smoke, right? Don't go and take up smoking just to try and study this, right? Go and find a friend who smokes and say, like, I'm just looking at this to understand how big interstellar dust is. But we can see those dust grains in these meteorites, and we can see they've come from individual stars, because different stars will make the dust grains in different compositions. And so that's going beyond just, say, like other people have suggested quite rightly, looking at the bulk compositions. You're actually looking at these grains and not just looking at the element abundance. You're looking at the relative different isotopes. So how many, say, heavier uranium atoms there are compared to how many lighter uranium atoms. That kind of stuff is an even more sensitive test. And what's really fun is when you look at the diagrams of them placing these isotopes, they go, okay, we know these come from these stars, these come from these stars. Where on earth do these all come from? Because we don't know. So there's still mysteries, and they're all coming up from the meteorites, which is really exciting.
That is really cool. Somebody asks, will the James Webb Telescope be able to detect chemical signatures in distant galaxies?
Yes. So interesting story about my research is that even though I started looking at the supernova progenitors, my colleague Elizabeth Stanway was doing a PhD at the same time, and she was looking at these high redshift galaxies. This was back 20 years ago when they were fuzzy red blobs. That's all we had on them. We would get a spectrum if we was lucky, but because of JWST, we'll actually be able to resolve and see those galaxies and actually get much better compositions. And so it's like completing the cycle, because everyone here has had these questions about, like, can this help? Can this help? Yes, because if you have this big picture, and it's the one thing both me and Elizabeth have really tried to concentrate on, it's like trying to understand and do multiple things. So we can look at supernova progenitors, we can look at the binary neutron star mergers, the black hole mergers, look at these distant galaxies. And we're just about to finish a review article about, how we link all this together and how we need to understand stars to understand those high galaxies. And it all comes down to composition. So it's going to be really interesting to see the results that come out of that. And because we've already got some already, but the new telescope will actually refine that. But at the same time, we're also going to be able to understand stars that produce dust and carbon and other things within our own galaxy. And so, using the same telescope to look at galaxies here and there, we can make this big picture about how all this works. It's really exciting.
That is really exciting. I really hope that's a successful launch. I think we all are.
Yeah.
I know some members have been holding their breath since it began being built many years ago. Why do we find heavy elements like gold or uranium on the Earth's surface? Why would they not be concentrated at the core of the Earth?
Yeah. Why do we? Well, in theory, all the iron should be at the center, and it's because of that horrendous thing called chemistry, I would guess. Is that it's one thing to say everything is molten, but things would have cooled off. And how did the Earth form? And planet formation is an ongoing process, right? We still have asteroid strikes and meteorite strikes. So that's not where everything comes from, right? We can talk about Black Panther, where we know that they have the asteroid that hit that's got the vibranium, which doesn't exist. Anyway, vibranium metal that, so you can get metal out of meteorites that way. But it's probably because planet formation takes time. So the iron core, and there's probably some differentiation taking place, but at some point the planet gets to a certain size that even if you had more stuff on the surface, it can't get down into the center. And so, it sort of stays on the surface. That will be my guess where that is, because it's an ongoing process. But any light elements in the core definitely would have raised, because the temperatures in the core are such that, any silicon or oxygen down there will just get sent to the surface. And then it gets locked in because of chemistry.
Perfect.
But also, sorry, you have the mental, right? So you constantly have volcanic activity spewing stuff from the interior out to the surface. So that's the other thing that's going on.
Great. We have time for just a few more questions, and I'll just read them out. Is there any truth to the idea of carbon stars being diamond?
So to an astronomer, a carbon star is actually a star that's producing lots of dust. So it's one of those AGB stars that's producing lots and lots of dust coming out from it. So that's different. But if you're talking about a carbon star of just diamond, there are white dwarfs that when you look at them, we know they're crystalline and we know they've got a structure like diamond. They're not a pure diamond because it's carbon and oxygen together. But the fun thing about white dwarfs is some of them actually oscillate. And so if you study them and how they're pulsing, and the sound, basically it's sound waves traveling within them, you can see that some of them must be crystalline. And so some of them can be diamonds, of a diamond-like structure, I should say. And so we know that's the case, and it's really exciting. So yes, although I've just read The Expanse where they've got a diamond planet. That's the 8th book. So I'll come back next week and I'll let you know.
Perfect. How do magnetars form, and what is their density?
Yes, we don't know. So this is, again, everyone's asking questions about stuff we're trying to work on. So magnetars are neutron stars that are highly magnetic. And how do magnetic fields in stars form is complicated, and it's to do with rotation. It's all mixed up. And again, it's something that everyone is struggling with, especially how we form magnetars, because they're rare. Not every, I mean, the fields are like the most extreme magnets in the universe. So they form like normal neutron stars, but somehow they get a magnetic field baked into them. And so, you know, maybe, and the other question is like, maybe if you have two merging magnetars or a magnetar of a normal neutron star, do they give different elemental production? We just don't know. So yeah, magnetars are weird, but they're much rarer than normal neutron stars.
Of course.
Yeah.
A question from the chat. Can we deduce different conditions in the neutron star collisions if we could measure elemental ratios?
Yeah. So that's where some of that elemental stuff from asteroids may actually come into play, that some of that material may have come from different neutron star mergers. Actually, it's really cool if you look at, I tried to find a simulation, because basically you see when you do the elements, you get all these really heavy elements and they fall back. So the answer is that's ongoing work. But yeah, certainly it's the isotopic ratios that are the next complication beyond just looking at the different elements.
Perfect. Do we know how far away were the elements that make up the Earth created?
You can work out on average. So that's what that table, that periodic table is. It tells you roughly where they formed. And so you know that maybe they would have formed that long ago. We know that because the Earth is 4.5 billion years old, all the elements must have been made at least 4.5 billion years ago. But things that come from low mass stars might have been billions of years older than, say, things like oxygen, which would have maybe only been a few million years before that.
Cool. Just to finish off, do you have any other online recorded lectures that you have done in the past?
Probably. And I was thinking the other day, I need to actually get down to actually put some of these up and make a list of them. Not public talks, I think. I think there's probably a few of them around, but you can probably find them. Yeah. The answer is yes. I'd have to go and find them. And I will try and do that on my website, because it's really important. And yeah, because there's lots of science ones as well that I've given professional talks, but it's about the same stuff. And so it's always good to try and find out those talks as well. You might not understand everything, but you always get an understanding of some of the exciting things we're working on.
Well, that's great. Well, thank you so much. That brings us to the end of our Q&A session. I just want to take this opportunity to give you a huge thank you from all of us on behalf of the Royal Astronomical Society of Canada here at the Calgary Centre. It was an amazing talk, and I know it was thoroughly enjoyed by everyone here by noting the comments and the texts that I've been receiving on my phone and talking about how great it is. So thank you.
Thank you, and thank everyone. And yeah, I'm glad everyone enjoyed it. So thank you very much, and thank you for inviting me.